Good morning. Let's get started. So for this first one here, we are doing an alkylation at our beta position. We have this ethyl soft nucleophile here, so I'm going to draw this out with some quotation marks around it. We're going to have this attack at our beta position, shift these electrons over and up to our oxygen. This will let us generate our alkylation product. Which we can then reform our carbonyl and protonate. To generate our final product. Doing a more complicated version of this. With the diketone here. Throwing in a base. What do I have on the sheet? Carbon there. Okay, so we're going to pull off this middle proton that's between our two ketones. It's going to generate enolate for us. I'm just going to draw it with the negative on the carbon. This can do an addition to our Michael acceptor over here. We'll generate our Michael addition product. We can add H+ into solution. This will form our ketone. Oh wait, no, this is the wrong position, isn't it? There we go. And give us our final product. So in the earlier class, I also drew out LDA doing the same thing. If you have this kind of diketone here, so if you add in a small base, you get your negative here, but if you also add in a large base, you're still going to get the negative there, no matter what. The reason behind that is just your pKa argument. So this proton here, this middle one between these two ketones has a pKa of roughly 9. Whereas even with a large base, these external ones, the less hindered ones, because there's only one ketone next to them versus the two ketones, they have a pKa of around 19. And pK is a logarithmic scale, which means that this is 10 to the 10 more acidic than this position here, which is like 10 trillion times, something like that, more acidic at this position. So your small base and your large base argument isn't going to matter at this position because it's so dramatically more acidic. Okay. Our next one is our storic enamine synthesis. So in our first step, we are going to make imine that is positively charged. We're going to need to pull off the proton in order to make this neutral. So we have two different alpha positions. One of them is secondary, one of them is tertiary. This is a pretty large base, so it's going to end up pulling off one of these primary positions. In order to make this enamine. And from here, it's just the reaction we've been doing. So we've got, oh, I used the wrong thing there. Oh, whatever. This Michael acceptor, I realized on the last one, for what I originally drew, I didn't have this methyl here. So we can make that into an H. All right, so Michael acceptor. Electrons from our nitrogen can reform that imine, do an attack. Alkylate at this less substituted position. And then adding in H3O plus is going to remove this amine as well as protonate. Our carbonyl is going to come down and protonate at this position, giving us our ketone back, as well as this other ketone here. I'm gonna do this one with LDA just to kind of reiterate that point I talked about a second ago, is that it doesn't really matter what base you use. Still gonna have the same first step. Just gonna make our enolate between our two ketones. We can do an attack on our Michael acceptor. this will generate our negatively charged addox here. We can reprotonate with H3O plus to reform our carbonyl and get to our final product. All right, and the next one I gave you the same first step to make things easier. So we're doing a Robinson annulation. Our starting material is the same thing as the last one. Our first two reagents are the same, so NaOH. This Michael acceptor here. The difference is that we're at NaOH and heat at the end. So our first step should give us the same thing. We just did it. It'll be this product here. So that's our Michael addition product. From here, we need to do an aldol condensation. So we are going to, there's two different sets of protons here. If I was to pull off this proton here, do an attack on this carbonyl center, I would make a 1, 2, 3, 4, 5, 6 membered ring here. Versus if I pulled off of this proton and it attacked, I'd make a 1, 2, 3, 4. We talked about a while ago, 6 membered rings are dramatically more efficient than 4 membered rings. So adding in NaOH is going to get us to goes up. Most likely this enolate here. I'm going to draw it as the other resonance structure for the next step, just to make it a little easier to see how big your ring is. Although these do always make 6 membered rings. So this is just the other resonance structure. I just put these electrons down. If I have this negative charge here attack at this carbonyl here, I will form a 1, 2, 3, 4, 5, 6 membered ring because I'm making the bond between this negative and this carbonyl here. So we just have to count the number of carbons between those two. Should give us a structure that looks so carbon 5 is this ridge head, which still has this on it. 4, 3, 2, 1. 2 had our carbonyl here. Carbon 6 we attacked, so now that should have an OH. From here, we're in NaOH and heat. We're going to pull off the proton that's closer to the ketone between the alcohol here. Do a little cyclic mechanism. So we're going to grab this H, make our double bond. The other oxygen is going to grab the other H. We'll form an aldol condensation product. which should look like this. So this is our Robinson annulation. It's a pretty long reaction compared to everything else we've been learning. All right, so let's move on to chapter 22. We're going to get through all that we're going to cover of 22 we're going to get through today. The end of 22 is those diazonium reactions we talked about for exam 3, so we're not going to redo those for this exam. I'm going to start with 22.4. We're not going to go over the nomenclature or the acidity. Preparation of amines. So you guys already know how to make amines. Most of this will be reviewed today. We take an alkyl, so this bromopropane here. We throw in NaCN. It's going to do an SN2. Add our nitrile group, and then throwing in LAH. And water. Will let us, let's make it amine. So we took this CN, we added these two H's to our carbon, and then these two H's to our nitrogen here. So typical reduction using LAH. We're going to do a lot of today. Another pathway we could go to get to an amine. Be very similar, throwing in magnesium, CO2, H3O, plus can give us a carboxylic acid. We want to make an amide, SOCl2, followed by ammonia. And then from here, we're just doing what we were doing before. So LAH can reduce this. Oh God, running out of space there. And give us this butylamine here. So both of these reactions, you're starting with this bromopropane. You're ending with butylamine, which means that you added a carbon. If we want to do this without adding a carbon, there's a couple of different ways. The most simple way is to do what's called going through an azide. It's gonna be really similar to this CN concept, except instead of NaCN, we're going to use NaN3. Our N3 can act as a nucleophile. I'll do an SN2. I'll go through the mechanism in a minute. Well, that part of the mechanism is very simple, but we'll generate this azide, which looks like this, and then throwing an LAH. Can give uramine here. This is propylamine, which means that unlike these two previous reactions which generated butylamine, we didn't add a carbon anywhere. So this first step, you added a CN, this you're adding CO2. Because you're adding N3, you're gonna burn two of them off. This is just adding one nitrogen directly, so you're not adding any carbons to make this. So for this to happen, we are going to take our N3. So this is mechanism 22.1, which is really the only mechanism we're going to talk about. They call it azide synthesis, even though you're making the amine. Oh God, I can't spell today. There we go. So our NaN3 does our little SN2 attack. From here, your lithium and aluminum hydride, so AlH4 can donate a hydride to this nitrogen. It'll neutralize this positive nitrogen in the middle. From here, our negatively charged nitrogen is just going to close to make N2 gas, cooking out this N. H minus, which in the last step we add H2O. So we can pick up that proton off of this and make our amine. Let's do the Gabriel synthesis next. So this is one way to make an amine directly. The other way is through what's called the Gabriel synthesis. So what this is going to involve is a reagent called phthalimide. There's kind of this diamide here. Marker's kind of dying. We add in NaOH to it. We can pull off that proton. This can then attack our bromopropane here. Do an SN2. We're going to add it to this phthalimide. And then from here, we can reduce off this whole group with either H3O plus, which will give us dicarboxylic acid, and our amine, which is what we actually care about. Or if we use hydrazine, we'll form our amine plus this hydrazone, I believe. But the part we actually care about is this amine here. So another way to make an amine. I guess I'll do that last. Yeah. All right, last way to make amines is through reductions. So something we talked about in chapter 19, I believe. So if you take a ketone, throw in H plus ammonia, we can make an imine. And then from here, if we want to make a primary amine, all we need to do is throw in LEH, as you might expect. And this can give us our amine. We can do the same thing with secondary and tertiary, or to make secondary and tertiary amines. So throwing in a primary amine instead, like this ethylamine, will let us make an ethylamine. Throwing in LAH and water can give us this secondary amine. Same thing with although it's a little different, secondary amine. So let's do this asymmetric one here. So we're going to make an imine or eamine first. But then from here, we're just throwing an LAH. And we can make this tertiary amine. So straightforward concept, make an amine, throw an LAH, you can get your amine. All right, last reaction I'm going to cover is going to be alkylating amines. So once we have this amine, if you want to do an alkylation, It's very straightforward. So let's take this propylamine we've been dealing with. It's a pretty decent nucleophile. If I throw in methyl iodide, the lone pair for my nitrogen can do an attack. No, positive charge. We'll lose that proton in solution. And we can do an alkylation. If you keep throwing in methyl iodide, you can keep doing this. So you throw it in once, throw it in again. Throw it in the third time. You can make the positively charged version of this. Like so. Bit of a review of how to make amines. So starting with CN. I don't like this marker. Throwing in LAH, and most of these are going to involve LAH. Gives us our amine. Same thing with an amide. Throwing in a azide, sodium azide. Followed by LAH. Also give us this amine. Taking our phthalimide. Adding in NaOH. Our alkylating reagent. Followed by, let's do hydrazine here. It is going to get us to our amine plus this byproduct. And then finally, ketones. Either make an imine or an enamine. Throwing an LH. And get us to our final product. All right, so that is all the material we're going to cover in this class. On Friday, we'll do some synthesis problems. Monday, we'll do some exam reviews. Wednesday, you'll have your exam 4. The other Friday will be final exam review. And then at some point in time, you guys will have your final. There are exam review or practice exams for 4 as well as the final. The final is very similar to just normal exam. You have more time on it, so I make you do both synthesis, both mechanisms, and both NMRs. But that's really the only difference. So I will see you guys on Friday.